So that means I'm going to need your attention and ask you to stop the side conversations, please. If you absolutely can't, then go someplace else. Okay, here we go. These are parent functions. Which one's this first one? Of our 6 parent function, which one are you seeing here? If it has not been shifted or stretched or anything, this is a sign. Y equals sine of x. And they're asking us to label. I just specifically want to label a couple points here. What are these 2 y values that I've just marked? This is 1 and this is -1, and sine falls entirely between that. And here's 0, and this would be the end of one period. How long is the period for sine parent function? 2 pi, which I'm hoping you, as soon as you say that, you're making that connection between, oh, that's 2 pi is all the way around the circle once, and then things start repeating themselves. If that's 2 pi, then this is pi over 2. And this is pi. Sorry, getting ahead of myself. That's pi. And this is pi over 2. And this is 3 pi over 2. Otherwise known as 90, 180, 270, right? Okay. This one, sine, cosine, tangent. What are we looking at here? This is cosine. And it goes from 0 to 2 pi as well. So it would have the same markings, pi over 2, pi, 3 pi over 2. And I'm not marking my negative sides, but if we need it, we'll come back to it. How about that last one? After all your practice graphing tangents and cotangents, can you tell the difference between them? This is a tangent. What do you see that helps you know it's tangent? Yeah, so tangent is increasing where cotangent is decreasing, right, over its whole domain. The other thing that my students will cue in on is a tangent, if it's not shifted at all, begins and ends at a x. One period of tangent begins and ends at an x-intercept and has an asymptote in the center, where one period of cotangent begins and ends at an asymptote and has an x-intercept in the center. So, so here is tangent x. And same markings. That's 0. This is 2 pi. We'll call that good. So here's the big thing for today. We're going to talk about inverse functions, and I'm going to unveil some small lies that you've been told about inverse functions. Not lies. We've withheld some information. We talked about that before. Tell me, do you guys remember when we talked about inverses back in chapter 1? Do you guys remember we reviewed vertical line tests? Remind me, what does the vertical line test tell us about a function? Oh, or a graph. Sorry, spoiler alert. If it's a function. What does the horizontal line test tell us about a graph? If the inverse is a function, okay? So can you please look at our sine, cosine, and tangent graphs and tell me, is it possible to have an inverse function for either of these 3? The answer is no. They both fail the horizontal line test like miserably. It's going to cross an infinite number of times. So if we take this as our sine function, there's no way we can have an inverse function for it. So, but we need to be able to do an inverse on these functions. These are too important for us to just be like, no, they don't have inverses. So we're going to do a little trick that happens a lot in math. We're just going to say, we're not going to look at the whole function. We're going to focus our attention on just a portion of it. We're going to do some chopping. And we're going to chop it strategically so that it does have an inverse function. So what I would like for you guys to do is look at this and tell me, if you were going to chop on the left and on the right and just preserve one section of this function that would have an inverse, where would you chop it? So I'm hearing 0 and 2 pi. Is that going to pass the horizontal line test? Nope, we're still going to fail. 0 and pi over 2. Hang on a second. 0 and pi over 2. Now, would that pass the horizontal line test? It would. Am I catching the whole range of my function, though? I'm only getting kind of the top half of it. I'm not getting any of the negatives. So give me something else. Negative pi over 2 to pi over 2. That's getting the whole all the way down to negative 1, all the way up to positive 1, and it's going to pass the horizontal line test. So if you were in charge however many hundreds of years ago when they decided where they were going to chop it, is that how you would vote? Yep, that's what they picked too. We're going to pick just this portion. So in order to have an inverse for sine, we are only going to look at the portion of the sine function where x is between negative pi over 2 and positive pi over 2. So we're not looking at the whole sine function, we're just looking at this one little place. And please, when you draw that little piece of it, make sure that you're sort of flattening it out at the top. All right, they picked the same thing. Now, did they have to do that? No, they could have done pi over 2 to 3 pi over 2. Or they could have done 3 pi over 2 to 5 pi over 2. That would have worked. They could have done negative pi over 2 to negative 3 pi over 2. Why do you suppose they chose why did you choose that one? It involves the origin and the y-axis. Yeah, that's probably why they chose it. I don't know for sure. I wasn't there. I'm not that old. Cosine. How would you chop cosine? If you were in charge, how would you chop it so that we get the full range from negative 1 to 1 and it's going to pass the horizontal line test? 0 to pi. Okay, we're all on the same page here. Yeah, for sure. For sure. So we're going to go 0 to pi. Again, make sure that you're getting it's sort of flattening at the two ends here. So for cosine, we're looking at cosine, but only the portion between 0 and pi. How about tangent? The first little, give me some angles. Negative pi over 2 to pi over 2, like between those two asymptotes there. Yep, I like that. I like that, and that's exactly what they chose too. Now this one's kind of interesting. Can we do the tangent of negative pi over 2? No, how do you know? There's a vertical asymptote there. Can we do the tangent of pi over 2? No. So it's going to look a lot like this with one small change. It'll be just less than. So negative pi over 2 is less than x is less than pi over 2. I think I might have screwed that up second period today. Double check and fix that on Monday. All right, back in, there's a couple important points here that I kind of missed. It would go through one kind of halfway in between there and halfway in between there. We'll need that in a second to graph. Back in chapter 1, you guys graphed inverses of some wacky looking functions. Do you remember what you did with your points, with the x and y coordinates of your points when you're graphing inverses? Just flipped them, right? So let's do this. We've got our sine. We're going to graph inverse sine. Look at these 3 points. Flip your x and y coordinates. I'm going to do, I'll tell you what, I'll do the origin for you. 0, 0 becomes 0, 0. You're welcome. You do the other 2. Pi over 2 comma 1 becomes 1 comma pi over 2. Negative pi over 2 comma negative 1 becomes negative 1 comma negative pi over 2. And in our original sine function, it was sort of flattening horizontally. This one's going to flatten kind of vertically at the ends. Looks kind of the same, just like sort of flipped on its side. It does look a little bit like x to the power 3, except x to the power 3 would keep going forever and ever. This one cuts off. This is it. This is the entire inverse sine function. All right, do the same for cosine. This one doesn't go through the origin. Hi. Thank you so much. What do we got? 0, comma 1 is going to become 1, comma 0. Pi over 2, comma 0 becomes 0, comma pi over 2. Pi, comma negative 1, negative 1, comma pi. It almost looks like a shifted and flipped, shifted and reflected version of the inverse sign. For inverse tangent, we'll do the points, but also the asymptotes. What do you suppose is going to happen to those two vertical asymptotes? They're going to become horizontal asymptotes. Origin. Okay, this is like pi over 4, comma 1, so that would be right here. So you're going to have those 2 points as well. All right, what questions do you guys have at this point? Inverse tan, does it kind of look like a log? Yeah, kind of. Yeah, a log would have logs have a vertical asymptote. So kind of up to here it does.
It looks more like a rotated cube.
Looks kind of like, yeah, or a cube root. It kind of looks like a cube root a little bit. All right, we're going to play a little game. You guys have your calculators? Grab your calculator. I'm going to give you something to punch into your calculator, but here's the rules of the game. You may not hit enter until I tell you to hit enter. That's cheating. Okay, so I'm going to tell you what to type in, but you may not hit enter until I say go. Okay, we're going to predict. This is called predict the error. Okay. You ready? First of all, make sure you're in degree mode. I'm sorry, radian mode. Radian mode. Check that you're in radian mode. Actually, I don't think it matters. Could you please type in the inverse sign? Hey guys, can you please stop? Thank you. Can you type in the inverse sign? Remember, you're not going to hit enter. You're just going to type it in. The inverse sign of 1.2. Now, spoiler alert, when you hit enter, you're going to see an error. The game is predict the error. You guys have seen lots of errors happen on your calculator. I don't know if you've ever paid attention to what the error codes are. Anybody want to guess what the error code is going to be? Error what? Syntax error. Good guess. And that happens a lot, but this is not a syntax error. Domain error. Because why? Is 1.2 in the domain of the inverse sign? No, it's past it. 1.2 would be right here. We don't even have it. So go ahead and hit it. It's going to be domain. Domain error means that you put something into a function that does not belong in that function. Okay? I got a challenge for you. Can you get a domain error for me doing a inverse tangent? See if you can come up with a number to stick inside that inverse tangent that's going to give me a domain error. Pi? Does pi do it?
No.
Try some really, really big numbers. Try some really, really small numbers. Try some negatives. I'm just curious. Data type, not domain. I want a domain error. Tell me why, as long as we give a real number, tell me why you're never going to get a domain error for inverse tangent. Because the domain is everything. There is nothing that's going to break this function. There's no x values that are going to break it. All right. The big thing that I need you to know here is that these inverse trig functions have some limitations both on their outputs and their inputs. And that's going to come into play when we actually start doing some problems. So this next part on the back is going to be super, super important. This table that we're about to fill out is probably the most important thing from today, and you're going to end up memorizing large portions of it. Actually, there's not that big to begin with, but you'll end up memorizing the whole thing. You might need to flip back and forth to look at these three graphs here in a moment. So, but flip over. I'm going to walk you through the inverse sine column, and then I'm going to ask you guys to fill out the other two. Okay? So here we go. Tell me, what is the domain of inverse sine? Inverse sine, we're talking about how far to the left and how far to the right. -1 to 1. Brackets or open or parentheses? -1 to 1, both are included. All right. The range goes with the outputs are the y values. I'd say the lowest it goes is -π/2, and it goes up to +π/2. So the range is -π/2 to +π/2. Those are angles. Inverse sine is going to spit out an angle. And it's going to be useful for us to think about quadrants because we'll be doing some reference triangles with our work here. So tell me which two quadrants are covered by the angles that range from -π/2 to +π/2. Give me one. Give me one. Quadrant 4 and quadrant 1. Yeah. Quadrant 1 and here's -π/2. Here's 0, and then we go up to +π/2. So quadrants 1 and quadrant 4, if we're drawing a reference triangle for inverse sine, we're going to be stuck in those two quadrants. Why? Because we decided as a class, in agreement with the mathematicians that came before us, that that's where we were going to chop off a sine so that it had an inverse from -π/2 to +π/2. I need you guys to go ahead and do the same thing for inverse cosine, inverse tangent, please. I'll give you a few minutes. We'll come back together, compare answers, and then we'll move on. Are we in agreement on inverse cosine? All right. Did you guys notice that inverse sine and inverse tangent are pretty similar? The domain's different though, isn't it? This domain we said it could be anything. What's different about the range? It's still -π/2 to π/2, but there is an important difference. We don't include those two because why? That's where they were originally vertical asymptotes, and then we did an inverse, and now they're horizontal. The quadrants would match, though, wouldn't they? -π/2 is still here, up through +π/2. So we're still talking about quadrant 1 and quadrant 4. So when we're talking about inverse trig functions, there's one quadrant that feels left out, never gets included. Quadrant 3 never does. And there's one that's always included, which is quadrant 1. Keep that in the back of your mind because we're going to talk about the big lie that you learned in geometry here in a moment and why it really wasn't a big lie. Okay, let's do some actual, I'm sorry, did you have a question? Why is quadrant 3 excluded? Why is quadrant 3 excluded? Well, we decided we were going to chop. We never included it. When we decided where we were going to chop, quadrant 3, it would be this spot right here. We never included it. So, we were able to get, using either quadrant 4, quadrant 1, or quadrant 2, we were able to get one full top to bottom for both sine and cosine and tangent. So, yeah, I don't know. I don't know if there's any, there might be more significance than that. All right, hey, there's a whole bunch of side conversations going on. Can we pause those, please? We're going to get into some problems here. They want us to do these with reference triangles. I would like you to do them with reference triangles. So here we go. Can you guys please draw me an x and y axis for this first one? this table is kind of your key to success here, and especially these last two rows, okay? So, hang on just a second, please, and I'll answer questions in a moment. So we need to pick which quadrant we're going to draw our reference triangle in. And we're limited in this one because it's an inverse sine. There's only two quadrants that we can use for inverse sine. They are this one and this one. Those are our two choices. Now, if inverse sine of this thing, this ratio is positive, where is sine positive? Between these two. This one. Okay, so here's our reference triangle. It needs to be in quadrant 1. The reason it was in quadrant 1 is it has to be in one of these two. And the fact that the ratio is positive tells us it has to be in the top one. So let's stick some values on here. We've got sine, which is opposite over hypotenuse, so root 2 over 2. And our goal is to find the reference triangle. Or, I'm sorry, not the reference. Our goal is to find the angle. Now, in this one, in quadrant 1, the reference angle is the angle, right? You guys know what I mean when I say reference angle is the angle? When we were talking about the assignments here a minute ago, remember how this is my reference angle, but that's not my answer. My answer is the angle starting at 0 going around. And the nice thing about quadrant 1 is the reference angle always is the angle. We don't have to do any translation or anything like that. Question?
Okay, isn't one of the triangles that we did, it was like the 44, 40, or 45?
It is a 45, 45, 90 triangle.
Because there was like root 2 over 2.
Mm-hmm. Yes. So if we divided everything by 2, we would see one of those.
Oh, okay.
Yep. So there's two ways that I think of this, and you're going to start getting used to this version too. Root 2, 2 is a 45, 45, 90. I could divide everything by 2. This would get a 1, and this would be root 2 over 2, which is why I asked you to memorize that one. Or I could divide everything by root 2, which would make this 1. Do you guys know what you get when you divide something by its root? You get its root. 2 divided by root 2 is root 2. So this becomes 1, this becomes root 2. It's definitely a 45, 45, 90 triangle, okay? So the angle is 45 degrees, which means my answer is going to be, let's give an answer in radians. 45 degrees is pi over 4 for the win. All right, let's try this next one. Inverse cosine. Inverse cosine narrows this down to two different quadrants. Actually, one of them is the same. First and second this time around. Which one do I want to choose if my ratio is negative? Second quadrant. All right. So we're going to use the 1 and the 2 to come up with our reference angle, but that's not going to be our answer, right? Our answer that we're going to give here is going to be the angle that gets us to that position from 0. So we'll have to do a little bit of work, but we got this. We got this. So ignoring the sign because we already used that to get the reference, it's 1 over 2 and it's a cosine. Cosine is adjacent over hypotenuse. Adjacent was 1, hypotenuse is 2. I sense a 30, 60, 90 triangle coming on. Is our reference angle the 30 or the 60? 60. If that's 60, then the angle that we want is 120, right? These would add up to 180, so that's got to be 120, aka 2 pi over 3. Yes?
Wait, how come you're finding the, how come you're finding the 120 in this triangle, but you're finding the angle?
Great question. So this angle is called a reference angle, okay? We're going to talk about why do we do these reference triangles? What's up with the rule about why it has to connect to the x-axis, and what's up with the rule that the angle has to be the one that's at the center? We'll talk about that in a lot more detail next unit when we're like picking apart the unit circle. For now, I'm hoping you'll just trust me on that. The deal, though, is that because of those two rules, any reference angle that you have in the first quadrant will also be the angle. The angle always gets measured from 0, right? And if you're in the first quadrant, by the rule that it has to connect back to the x-axis, this is always measuring from 0 also. Does that make sense? But if it's not in the first quadrant, then you're going to have to do some adding or subtracting from 180 or 360 to get your reference angle, or to get your actual angle. Thanks for that question. By the way, we got our calculators out. We should probably be checking these, huh? If you were doing this on a test, this would be a really easy check. You would just make sure you're in radian mode, type in inverse cosine negative 1/2, hit enter. Now that's a big old decimal. Is that the same as 2 pi over 3? I don't know. Type in 2 pi over 3 and let's see. Oh yeah. So you're going to be doing some even numbered problems on your assignment today. I want you guys using your calculators to check. Okay. Get in that habit. All right. See what you can do on the next two. I will tell you there's some trickiness about these two. There's some trickiness. Give them a shot. All right, inverse sine, so we're stuck in these two quadrants again. Ratio is negative, so it must be in the fourth quadrant. Reference angles here. Opposite over hypotenuse. That's that 45, 45, 90. You'll get used to seeing that root 2 and that 2. 45, 45, 90 triangles. So my reference angle is 45 degrees. Am I going to rotate from 0 positive all the way around? Nope, nope, that's going to be too big. It is negative 45 degrees. That fits into my range. Negative pi over 6. Negative pi over 4, rather, for my final answer. How many people were able to get negative pi over 4? What questions do you have at this point? All right, we're moving on. Here comes the big lie. You ready? Don't miss this one. So we've talked about this before. This is part of education. Is your teachers have to decide how much are we going to try and drop on you at one time, and like, can we not cut some corners, but can we hide some details that are going to make things kind of messy for you? So let me ask you this. If I had asked you 2 years ago when you were in geometry, if I were to ask you what my final answer is going to be here without doing any calculations or anything, what would most of you probably guess? 4 pi over 3, because what were you told about inverse cosine and cosine back in geometry 2 years? They cancel each other out, okay? And here's the truth. Sometimes they do, but sometimes they don't. So let's work through this. And you'll see why this works and why that was an acceptable kind of fib to tell you back then in just a moment. But let's do this. So what I'm going to do is I'm going to evaluate this from the inside out. So my first order of business is to figure out what the cosine of 4 pi over 3 is, and then I'm just going to take that and put it in here, okay? Now some of you are going to end up having this memorized, but most of us right now probably are going to need to sketch a reference triangle. And most of us are probably also going to need to think about this in terms of degrees. How many degrees is 4 pi over 3? Pi over 3 is 60, and 4 of those is 240 degrees. So get me a reference triangle where the hypotenuse is at 240. That's 60 degrees past 180, right? So 30, 60, 90 triangle, 1, 2, root 3. Again, this should be getting pretty quick. I ask you to draw a reference triangle. You should be able to get some sides in pretty quickly. All right. Oops, I forgot my inverse. So what is the cosine of 4 pi over 3? First of all, is it positive or negative? Cosine in this quadrant is negative. Cosine is adjacent over hypotenuse? Yes. Negative 1/2. We're not using the calculator here yet.
But I'm using a previous
Yes, we have actually already done this one. Okay, so we're going to do the inverse cosine of negative 1/2, and I did not notice this before. That's some good noticing. We actually already did the inverse cosine of negative 1/2. It's a little further up the page, but I'm going to do it again, just for practice. So inverse cosine of negative 1/2. Inverse cosine must be in which two quadrants? First or second? Which one am I going to choose if my ratio is negative? The second one. Reference angle is here. Cosine is adjacent over hypotenuse, so 1 and 2. And I recognize, oh, that's a 30, 60, 90 triangle. There's a root 3 in there also, which makes my reference angle the 30 or the 60? 60. But my answer is not going to be 60. That's the reference angle. The actual angle in the standard position is 120, aka 2 pi over 3. So you'd think that those two, inverse cosine and cosine, would cancel and we get 4 pi over 3, but we actually get 2 pi over 3. So inverse cosine and cosine do not always cancel each other out, okay? But I want you to think about this for a second. And some of you are just kind of finishing up here. Maybe you're working ahead, but please pay attention to this. I want to try and justify why we fibbed to you back in geometry. Back in geometry, when you guys were learning trig, SOHCAHTOA, all of the triangles were of a particular type. They were always what type of triangle? Right triangles. And right triangles only have angles that are what size? What's the biggest angle you can have inside of a right triangle? Well, the 90, right? And then the other two angles both have to be less than 90, right? Because they add up to 180. So if we're talking about angles inside of a right triangle, if we had introduced you to reference triangles back then, our reference triangles would have always been in the same quadrant. They would have always been in quadrant 1. They would have been between 0 and 90 degrees. Agreed? That's why we didn't do reference triangles back then, because we didn't talk about obtuse angles or negative angles or anything like that. It was always between 0 and 90. And as long as my angle is between 0 and 90, these things will cancel each other out. Okay? Because your reference triangle will end up being the same in the same spot. Okay, so we sort of fibbed you and said, oh, these things cancel each other out. For the purposes of that time, they did. But now we're in pre-calc, and we're going to be dealing with some triangles that are not right triangles. Next unit, we'll be learning how to solve triangles using law of sines and law of cosines, and you're going to love it. But all right, let's try another one. Let's try another one here. If you haven't already, work from the inside out. We're going to do an inverse tangent first. Whatever we get, then we're going to do the tangent on that. So inverse tangent. Inverse tangent, what we just learned today is that inverse tangent, we got to be thinking about angles only in the first and fourth quadrant. My ratio is negative, which means it's which of those two, first or fourth? Fourth quadrant. We got ratio of 1 over 1. Tangent is opposite over adjacent. So those are both 1s, which means I think we're looking at a 45, 45, 90 triangle, folks. Reference angle is 45, but we're not going to use that. We need something between negative 90 and 90. So let's think of that as negative 45 degrees. But we'll do it in radians, which is negative pi over 4. So I'm going to simplify this a little bit. We've still got that tangent on the outside, but all that work that we did, we turned this into negative pi over 4. All we got to do now is evaluate the tangent of negative pi over 4. So let's draw a new reference triangle, or can we use the same one? Negative pi over 4 is this spot, right? So this reference triangle will still work for us this time. We're doing a tangent in the fourth quadrant. Is our answer going to be positive or negative? Negative, and give me some sides. Opposite over adjacent, 1 over 1. Oh my gosh, it's negative 1. Hey, they canceled each other out that time. Nice. Sometimes they do, sometimes they don't. All right. Hey, have you all seen arc sine before? I'm sorry, question about this one first. Oh, yeah. Yeah. I'm going to ask you on the test to show work using reference triangles, though. Yeah. Yep. Or else I'll give you something where the answer is going to be something like this. And you do it on your calculator, you're going to get some big old decimal or something. So, yeah, I need you to be able to do this because this is going to affect some stuff that we're doing in the next unit. Okay, I want you to internalize this idea that these inverse functions can only give us angles in certain ranges is kind of be a big thing later on when we're solving equations with them. Yes. Other questions before we do the last one? Arc sine, have you seen this before? This is kind of a more old-fashioned way of saying inverse sine. It means the same thing as sine with the little negative 1. I actually kind of prefer this because sine with the little negative 1 makes you think that it's 1 over sine, and it is most definitely not 1 over sine. But the thing that's kind of weird and I'm not a huge fan of is next unit, you guys are going to be thinking about sine squared of x. And that does mean multiply one copy of it by another. So this is an exponent, but this is not an exponent. I don't know why they chose to use this notation. It used to be arc sine. If you're a programmer, it's just a sine, A-S-I-N. Anyways, I'm challenging you guys to try this one on your own. I'll give you an answer. See if you can get there. Get my attention if you need some support. The assignment is on Canvas. The assignment has a bunch of even numbered problems. Make sure you're using your calculators to check your answers. Like was just pointed out, we can definitely type these things into a calculator and let it do all the work for us. Make sure we can do it by hand too.